L'Hopital's rule, or as I used to call it, hospital's rule. Indeterminate form are mathematical expressions that do not have a clear mathematical value. These usually arise in calculus when evaluating limits. The most common indeterminate form include the following: the indeterminate quotients, indeterminate differences, indeterminate products, indeterminate powers. Under indeterminate quotients, we have 0 over 0, infinity over infinity. Under indeterminate products, we have 0 times infinity. Under indeterminate differences, we have infinity minus infinity. Then for indeterminate powers, we have 1 raised to infinity, 0 to the power of 0, infinity to the power of 0. These indeterminate forms are dealt with by using L'Hopital's rule. Let's evaluate the following limit and see how the rule works. Let's start by breaking down the limit expression and evaluate the expression separately at x infinity. We see that the evaluation of the expressions gives infinity to the power of 0, which is one of the indeterminate powers. For indeterminate powers, we start by letting the limit expression be equal to a variable. Introduce natural logs on both sides. Apply the power rule of logarithms. Simplify and evaluate the limit. This time we get an indeterminate quotient infinity over infinity. We apply L'Hopital's rule. Differentiate the numerator and the denominator separately. The derivative of the natural log of x is 1 over x, and the derivative of x is 1. Now we rewrite the limit as the derivative of the numerator over the derivative of the denominator. Simplify and then evaluate the limit. Since this time we get an expression that is not one of the indeterminate forms, exponentiate both sides to get rid of the natural log. In this question, we are required to prove that the limit evaluates to e. As with the last question, we start by breaking down the limit expression and evaluating the expressions at 0 separately. The evaluating of the expressions gives us 1 to the power of infinity, which is an indeterminate power. We let the limit expression equal y. Introduce natural logs on both sides. Apply the power rule of logarithms. Simplify and then evaluate the limit, which gives an indeterminate quotient 0 over 0. Apply L'Hopital's rule, differentiate the numerator and the denominator. Rewrite the limit as the derivative of the numerator and the derivative of the denominator. Simplify the expression, then evaluate the limit. The result is not an indeterminate form, we therefore exponentiate both sides to get rid of the natural log. Breaking down the expression and evaluating at x equals 1. The evaluation leads to the indeterminate power 1 to the power of infinity. Let the expression equal y. Introduce natural logs both sides. Apply the power rule. Evaluating the limit gives an indeterminate product, infinity times 0. We need to rewrite the limit in a form that will allow us to apply L'Hopital's rule. Evaluating the limit gives us the indeterminate quotient infinity over infinity. Now differentiate the numerator. Then differentiate the denominator. Note that in differentiating the denominator, you may use the quotient rule. It's just that I am not a fan of it, that is why I choose to convert the expression so I can use the product rule. Now rewrite the limit as the derivative of the numerator over the derivative of the denominator. Simplify the expression before evaluating the limit. Evaluating the limit gives yet another indeterminate quotient 0 over 0, which requires L'Hopital's rule. Differentiating the numerator requires the use of the product rule. Let's start by writing the product of the two functions. The structure of the product rule. We take the first function f of x and get a derivative. We get the second function g of x and get a derivative. Now using the structure of the product rule, we bring every expression into place. Let's do a little bit of cleaning up. Differentiating the denominator using the chain rule, after simplifying this part of the derivative, has the structure of the double angle identity. We write the expression as the derivative of the numerator over the derivative of the denominator. Simplify before evaluating the limit. Evaluating the limit gives us yet another indeterminate quotient 0 over 0. Differentiate the numerator and denominator using the chain rule. After simplifying the derivative over the derivative, evaluate the limit. Finally, an expression that is not an indeterminate form.